Okay, so for those of you who don't know it, the gEDA project is a suite of free software programs for electronic design automation. It has gSchem, a schematic capture application. It has gNetlist, which is a command line tool for creating netlists, which are lists of components and the connection between them. It has PCB for PCB layout, GURB for inspecting Gerber files before sending them to fabrication. And recently, somewhere in between those, connecting these Xorn. This talk is about what Xorn is, why it is there, and if maybe you want to use it. So I got involved with gEDA in 2009. I was using gSchem to add some, to create some simple schematics. And every time I would add a component, I would double-click it, and nothing would happen, because you have to select it and then press OK, which I knew, but it still was counterintuitive to me. So I created a patch which would be allowed to double-click a component and submitted it, problem solved. But then I wondered if it would be a good idea to put the component selector to the side of the main window as a dock, and if it would be a good idea to have a project browser where you could select files in the current working directory or a property editor. And then I realized that with the way the code is organized right now, this would be not easy. And that's probably the way why it hasn't been implemented before. So because the wish to have a common user interface for both PCB and gSchem was around for some while with gEDA, I decided to work on that. And 4 years later, I had solved most of the user interface issues. I had the library, doc, a project browser, and some other features which were nice to have, which didn't exist in gEDA right now. But I still hadn't connected this to the main gEDA code. And that is because I wanted to have a good scripting foundation, which would allow me to not duplicate any code which is not user interface related. And this scripting foundation didn't exist yet in gEDA. But in order to work on that, I would have to answer a few questions first. What is scripting? What purpose does it solve? And what are the constraints under which scripting is working? So in a proprietary context, an application is this big blob of code, and you can't inspect it, you can't change the way it works. But users who are more experienced usually want to automate the tasks done in an application. They want to chain the application's operations into more complex functionality. And also it may make sense to extend the user interface depending on the workflow for maybe simulation or importing a schematic into PCB. And obviously combine those two, create more complex functionality and extend the user interface with that. So what vendors do is they embed a scripting interpreter into an application and export the functionality of the application as procedures to the scripting interpreter. And then they add hooks at various points, for example, application startup or pressing a user interface button, saving a file, where user scripts are executed. So this is basically a way to regain some of the flexibility which is lost by not being able to modify the application in the first place. With free software, users can modify the package, so there is no need to do scripting. But there are a few reasons why it may be a good idea to do so anyway, because the high-level application, the high-level logic of an application is usually more complicated and more error-prone to express in a low-level language. So it may make sense both for the developers of the application and the users to have another language, a high-level language, to express this functionality. Also, if you ever worked with the developer console in Firefox, you probably know that it's really good for learning how the scripts work and for debugging. And it would be a nice thing to have that too in a gEDA application. And finally, today, most users will get the binaries from their distribution's package management. So it is a very important thing that they are able to modify the application without having to rebuild it. So you may ask, why not write an application in a high-level language in the first place? And actually, in most cases, that's a good idea. But there are a few problems with that. If the application does very data-intensive work, like bit shifting stuff, or this is much easier to express in, for example, C. And a solution for that would be to create an extension for the high-level language, which embeds which extends the language by this functionality, which is done in, for example, C. And you could write the REST application still in a high-level language and would not have any performance problems because the important data parts are written in C. Also, application startup time may be an issue. Depending on the machine, a script interpreter may take like a second to load up, and this is not always acceptable as a delay for a user interface to show up. So one approach to this would be to write the user interface in a, for example, C or C++, and then embed a scripting interpreter, which executes the rest of the application, the high-level code, which is written in a high-level language. Another point where there's a big difference between what's useful for proprietary and for free software is how do we deal with user-contributed code. With proprietary software, the vendors add this API and the users use it to add their scripts, but what they do with it is basically their own problem. It is not usual for user scripts to be to go back into the main application. In a free software context, a model where user code is contributed back upstream is usually much better. For example, the Linux kernel is really aggressive about this and tries to get things into the repository. This has a few advantages. Users will see the code if it's in the repository, but even more important, the developers will see this code. When a developer changes something and, for example, the signature of a function, can just grab the repository for lines who match this and can fix it right in the same commit. Scripting is often used as a way to move the responsibility for the contributed code from the users, from the application vendor to the users. But this doesn't make sense in a free software context. So by taking responsibility for the code, the contributors are not left alone with old incompatible versions, and the users have the not bit-written code, even if the original contributor is not around anymore in the project. And finally, there is a part which is which concerns the programming, because up to now, this looks like much more additional responsibility for the developers where they don't get anything back. But they do, in fact, get something back. And this is really a good thing because they need to worry less about what they are breaking outside the repository. So if you have a plug-in model where others have their own code living on their own machines, you usually define an API to have still some flexibility, because you would break everything if the add-ons would rely on the internals of the program and the internals changed. So if the code lives in a main repository, this is not necessary. You can have the code use the internals of the application and can just change the code along with the internals if the necessity is there to change anything. So in order to create a good scripting foundation, it is necessary to see what is a good idea to have for scripting in a free software context as opposed to proprietary software, because the models we know from there may not be very useful in a free software context. The most obvious thing probably is the functionality of the application should be available to use. And if you ever used GIMP for example, script foo, and have tried to run it from a command line, there is an option not to show the GUI, but it is loaded anyway. So when you run a GIMP script from the command line, it takes a very long time for GIMP to start up, which is not usually acceptable for command line tools. So the most the easiest approach to this would be to try to strictly separate between the GUI code, which is not loaded at all if there are any scripts executed, and the functionality which is available to scripts. This is, for example, how PCB handles this. But if you do this very seriously, what you are left with is a slim application which basically embeds a scripting interpreter and exports a lot of functionality and then runs a script. But if you have this, you could also have just made the part of the functionality of the application a library and invoke a scripting interpreter which then runs the script using the library. So you could restate this idea to have the functionality of gEDA available as one or multiple libraries, which can then be used by other programs without having to spawn another process. Another thing which would be a really good idea to have is the high-level code being able to operate on the same data in the same process as the low-level code. This has a number of advantages. For example, if you want to be able to switch which language to use according to which is appropriate for a problem, then there should not be the need to serialize the data, feed it into an external program, and deserialize it back. And also, it would make the difference between an external script and a high-level functionality of the application much smaller, because it would basically both do the same thing. It would execute some high-level code, and in one case in the application, and in the other case it has been invoked another way, but it's basically the same code. And also it would make an interactive console possible. So in order for this to work, what we need to have is a clean point where the low-level code and the high-level code can both access the same data without having to worry for each other's implementation details or private fields or whatever. So it is necessary to enforce a very strict object model where there are no fields private to some part of the application, so they can all in the same way access the data. And this from this follows that it is not possible to have, for example, notifications when anything changes, because it would mean that every part of the code would have to run these triggers, and if any part didn't run these triggers, then something would not be updated on the screen, or undone, or on undo and redo. So for this to work, we need to have a value-oriented data model, where we have a number of revision objects instead of this one file object. And if anything changes, the application just has a pointer on one revision object and can compare these revision objects and see what needs to be updated or what needs to be undone, redone. In order for this to be implemented in an efficient way, it would be necessary to encapsulate the storage code into a part of the application. So, for example, the high-level code does not have to query every object and iterate over it and see if it has the right property it's looking for. But it can run a high-level query like, please give me a handle for every object which has color blue, and move all these objects which fit this handle to another layer, or read all top-level floating attributes. So this is what I did. There is Xorn storage, which is this shared storage part of the application. It defines the revision type, which represents one version of the file. It represents it implements an object type, which represents the identity of an object, which is basically what you would have left if you you just showed me 5 minutes left. Is this? Oh. Okay, which is what would be stay selected if you changed the revision by undoing or redoing, and what would still be selected, and it defines a selection type, which is the same thing for a set of objects. In addition to this, it defines a set of data types which contain the data for an object, and this looks, for example, like this. This is a structure for a net. And you might notice that some very common things are not in this data structure. Like, for example, the bounding box of the object visually on the screen, or if the object is selected, or what nets this net is connected to, or what attribute objects are attached to this net. And this is because the bounding box is something which can be recalculated. There would not be a valid situation where the bounding box is changed, but the object parameters are not changed. And the selection is something which is only useful in an interactive context. And it would make sense to have an additional pointer to, for example, a selection object. So if the script wants to change the selection in addition to the contents of the file, it can update the selection object. And it would be possible to change the selection or not change it on undo redo by keeping track of a selection object or ignoring it. Attribute texts are visual objects on their own in gEDASLASgaf, so it makes sense to have them as individual objects and keep some track of the structural data. So there are dedicated libs on storage functions for looking up all attributes attached to one object, for example. Also, a question which is important is what data should be inside a revision. For example, symbols in gEDASLASgaf are usually embedded from a library, so the user does not expect them to be undone and redone when they undo and redo. And pix maps, there is no way to change a pix map from inside gschem, so this is a strong indicator that they should not be part of the revision. Paths, on the other hand, are objects which represent all the geometry which cannot be represented by simple line or circle or arc objects, for example, the arrow on a transistor, and they are modified by moving handles inside gschem. So this is not a trivial question, it's what makes sense in this context. This is how Xorn is currently implemented in Xorn. There is libs on storage, which I just talked about. Here is an example program which I will skip for time reasons. There is Xorn.storage, which are Python bindings for libs on storage. I decided for Python because it's a language which is relatively easy to learn as opposed to a scheme which is currently used in gEDASLASgaf. Here is an example for that. Xorn.gado, which is basically the parts of libgado which are interesting to use in another application, ported to use the new functions. There is a new file format. There's a command line tool Xorn, which offers all the functionality you would expect to be available on the command line. For example, converting a file from one format into another, or extracting symbols from a schematic file. gNetlist, which has been ported and refactored, so it's now a Python package and can be used from any application. And there is support for Guile, which is important because it allows users to use the old setup they have with executed scheme configuration files and maybe custom scheme code executed in the netlister, and it will still work. So if you're using gEDASLASgaf, you can use Xorn right now, for example, for writing scripts which manipulate schematics, writing a netlist backend. The most important restriction on this is gschem does not use the new libraries yet. So you can't manipulate the objects loaded into the editor. But you could, in theory, use a Python interpreter to edit a schematic file. You just wouldn't see what you're doing. The most obvious next step would be to use the new libraries in gschem 2. This is not trivial because libgado is the shared part of gschem and some other applications. And my approach so far has been to port the other applications to use the new libraries first. I've done this for gNetlist, which is probably the most complicated part, and started doing so for gEdRib and libgeda-cairo. But there are some problems, like, for example, gEdRib uses a GTK spreadsheet widget, which is not supported anymore. So it may make sense to duplicate the libgetter code and have for some time two versions around, one for the old tools to use and one so it can be merged back into gScim, so gScim can be updated to the new libraries. With PCB, it would obviously be also a good idea. I proposed a data structure for PCB on the mailing list, but didn't have time to pull parts of PCB out into the library yet. And for other projects, it may be interesting to use this approach too, or maybe even the same library too. And this would make it possible to have a common user interface which is used for several projects and applications. Thank you for listening.
Time for one quick question. A quick one.
Yes? Excuse me?
Could you do the same for KiCad?
If I could do the same for KiCad? Well, in theory, yes. In practice, I do definitely not have the time for that. But I could support you if you wanted to do that for KiCad.
Okay. Thanks, Roland, again.